So in this lesson, we talk about trying to apply Navier-Stokes equation. If you remember where we have derived, we derived from the conservation of mass, this one, and then we don't know why. Okay, they use that equation is similar to the Navier-Stokes equation, and then we also said that we have a Navier-Stokes Cartesian coordinates, and then we set our parameters and assumptions. Okay, I just talk about the important stuffs. So we talk about non-pipe system at first. We talk about the shaft. Okay, the shaft. Yeah, I think you remember already. And then we talk about Cartesian coordinates. When it is a non-pipe system, you use Cartesian. Okay, if it's a pipe system, you use polar coordinates. This is the first key thing I want to make known. Second key thing is that when you apply boundary conditions for non-pipe system, you have to first integrate twice and then apply boundary conditions. For pipe system, you have to integrate once, apply boundary condition, integrate again, apply secondary boundary condition. Okay. The third thing I need you to know is that when you apply boundary conditions, okay, apply those which everything is equals to 0. Okay, so example, when y is equals to 0, u is equals to 0, or in another case, the pipe case. Okay, hold on. Although when r is equals to 0, u is equals to capital U, but when it is in terms of, because when you integrate one time, right, when you integrate one time, you have partial u over partial r, so you can straight away input your boundary condition in order to cut away the c constants. So yeah, it's a little tricky, but just let you to know that try to pick the first boundary conditions where everything is equals to 0. Okay, so this is the one. And then the third thing is that for non-pipe system, okay, the plate itself, okay, I don't know where do I have the moving part is actually this part. It is moving. Okay, it's moving. So there will be a frictional force from the bearing wall. If you don't understand anything, you can go back to watch. Okay, I'm not gonna explain. But this is the key concept I want to make known. Because yeah. And then as for pipe system, it's a different one, right? For pipe system, you have two walls and you flush water inside. Due to the friction over these two walls, the particle would move slower, right? Particle will move slower. I hope you know what I mean. And this is the things. And then another thing is that before you apply any boundary conditions, okay, one key note you need to know when you try to decompose the Navier-Stokes equation. Okay, when you decompose the Navier-Stokes equation, okay, this is the template. Okay, if you don't know what it is just simply you sub in. If it's x-axis, you just sub in the u velocity and blah 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 u, and then x coordinate, and then u. If it's w, and then you just sub in w, you know, and then if it's z, that's all. Okay, and then one thing I need you to know is that you have to assume fully developed. Okay, when it is fully developed, then you can assume constant average velocity. This is where you can further, because when you put in your parameter assumption, you already so-called reduce the formula to this form. And then if you were to use this fully developed term, okay, you can further reduce into only these two terms over here, which you can expand on it. So this is mainly the key issue. And the last thing I need you to know is that we already cleared example 1. Okay, totally. Okay, everything is cleared. However, example 2, I only clear this portion over here. I'll leave. I don't know whether next lesson we'll really talk about the rest. But just briefly go through is that the volume flow rate we actually go through. You can actually follow this video, and then you just work it out. And then how the results of U and Q are affected by the pressure gradient. I believe you know the pressure gradient and understanding, although just to let you know my pressure gradient understanding is not good. Okay, I didn't explain well, so you should go and read it out if you should find out, and then you add into my comments. And then derive the shear stresses of the flow. We also derive the shear stresses. Okay, it's the same thing, just a little variations. And then where and what will be the maximum velocity of the fluid? I believe is at this point. Maximum velocity of the fluid. But you have to prove, I have no idea. What will be the average velocity of the fluid? You have to take the volume flow. I don't know, maybe you have to, I think you have to take volume flow rate and then divide across y, I don't know, you have to go and find it out. And then Reynolds number and entrance length. I think next video we will talk about it. So I'll see you in the next video. I mean next lesson the lecturer will talk about it. So next video I will see you. Hopefully he go through, and otherwise, yeah, we have more work to do. So now we have left only 30 page, right, topic 8. So I'll see you in the next lesson, and bye bye.